Lesson 40, the this pointer. To follow along with this lesson, you will need to create a new console project and add a new file named main.cpp to it, as we did in Lesson 1. When an object calls a member function, the member function is able to access the members of that object. This simple class contains an int member and has get and set functions. These functions are straightforward. In our main function, we create an int object. Then we call set to set its data member value to 3. After this, we call get. Executing the program, we see exactly what we expect. The outputted value is 3. We can have many instances of a class in one program. So how do functions like set and get know which object has called them? The answer is that the member functions are passed a pointer to the calling object. The pointer is passed in with the name this. In our example, this points to the object myInt. In fact, we should think of member functions as plain functions with an additional pointer parameter of the class type that the function belongs to. For example, the signatures of our set and get functions with the additional this pointer would appear as shown here. Notice that the this pointer is a constant pointer. Having a constant pointer means that the pointer cannot be set to point to a different object. However, the object that it points to can be changed, as we did in the set function. The this pointer is a hidden parameter, so we cannot see it. However, we can use the this pointer. Here we have the same code as before, except that we use the this pointer to access the member variable. Executing the program, we see that the code functions exactly as before. As our prior code showed, we did not need to reference the this pointer explicitly to access the member variables. However, there are many cases that we will see in the coming lessons where we will need to do so. In our next program, we have a simple class with a member variable named x. We also have a member variable function named set. The function set has access to 3 double variables named x. One is global, one is local, and the last one is a member variable. When x is set to the value of the argument, it isn't clear which x gets set by the assignment. In our main function, we declare an instance of myClass and call set with the value 4. Then we output the values of the global and member variables named x. Executing the program, we see that neither of these x values has changed. In fact, the local x value that we didn't output was changed. The local variable hid the member variable in this case. However, if we use the this pointer, the member variable will get set. This time, when we execute the program, we see that the member variable was set to 4. In our lesson on local and global scope, we stated that the variable with the most local scope hides the others. For completeness, we state here that local variables inside the function are selected first, then member variables, then variables outside the member function, like our global x variable. These scoping rules may be hard to remember. However, if you use Hungarian notation, many of these problems don't exist. Here's our program with our Hungarian notation. Since the member variable starts with an m, for example, it never gets confused with a local or global variable. That's another good reason for using Hungarian notation. We have one last example to help illustrate what the this pointer is. Here we have a simple class called thing. The class contains only one member function that returns the value of the this pointer. In our main function, we instantiate a thing object. Then we output the address of the object, and we output the value of the this pointer that is returned by our member function. Executing the program, we see that these values are equal. This last example demonstrates clearly that when we call the member function getThis, the value that is passed in as the this pointer is in fact the address of the calling object. This concludes the lesson.